Hello, in this video I'll be talking about how to apply Newton's laws to solve questions involving tensions and acceleration. So for that, let's try out with the first example. Let us say that we have a mass and we are applying a force on it. Let's call the force F and the mass is m. By Newton's second law, we know that the acceleration of this object is going to be the net force divided by the mass. The direction of acceleration is in the direction of the net applied force, which is towards the right. Now let's take another example, and now what we do is we have a pulley. Let's take this as our pulley, and now we have one mass here and one mass here. Let's call these masses m1, m2. There is no friction anywhere in this pulley, and the rope is now just slipping. When we release the system, the rope will slip. So that means the pulley will also not rotate. Now how to solve this problem? First of all, let us try to draw the free body diagram of each mass. Drawing the free body diagram for m1 first. The m1 weight is acting downwards. You have to draw tension always opposite to the mass. So that's how our tension goes. The number of tensions that you will take equals the number of string you have. In this case, because there is only one string, so we will take only one tension, not more than that. Now we have the equations. Now to write the equation of motion, we will write it as, assuming that m1 goes up, so the net force must be upwards. So you will say T minus m1g, that is all the forces which are acting upwards minus all the forces which are acting downwards, equals m1 a1. This is our first equation. Now let's try to write our second equation. But before that, we have to write down the free body diagram of m2. For m2 as well, you have the weight acting downwards and the tension going upwards. Now let us imagine that this thing, or mass m2, is all coming downwards. So in that case, the net force is acting downwards. So we will say all the forces which are acting downwards, that is m2g, minus all the forces which are acting upwards, minus T, equals m2 a2. Now if you try to add these two, we can eliminate T, and we have another equation then, m2 minus m1 times g equals m1 a1 plus m2 a2. Our aim is to find what is a1 and what is a2, but from here we cannot find it. We need at least one more equation to solve this. That equation will come from the constraint relation. We call that a constraint relation. A constraint relation is nothing but a type of relation that exists physically between the objects. So how to determine the constraint relation? We had this pulley, and these are the masses m1 and m2. After some time, this will be the situation. m2 will be coming downwards and m1 will be going upwards. To measure everything, we need a point of reference, and we would like to choose a point of reference that doesn't change with time, because then the accelerations and everything will be with respect to ground. So let us try to choose that point. We can choose it anywhere. We can choose it on the ground. Let's say this is our ground. We can choose the reference point on the ground, or we may choose it anywhere else, and that point should not move. So let's try to pick the point here on the pulley. Because the pulley is not moving, the point of reference is at rest. That means everything that we are measuring from pulley will be with respect to ground, because pulley is also not moving with respect to ground. Now how to do that? Let us assume at any time mass m1 is at a distance of x1 from our point of reference, and mass m2 is at a distance of x2 from our point of reference. Some of the length is also coming over this pulley. We don't have to worry about that, and let's call that length to be L. Now how to find the constraint relation? Constraint relation can be found out by using the fact that the length of the string does not change. That is, the length or the rope is inextensible. The rope is inextensible. So that means at any time x1 plus x2 plus L must be a constant value. This L is also a constant actually, because the amount of rope going over the pulley, that will also not change. Now what we do is we differentiate this equation. If you differentiate this equation, we will write dx1 over dt plus dx2 over dt. Now L is constant, so its differentiation will give us 0. On the right hand side we have a constant thing, that's differentiation will be 0. Because x1 is decreasing with time, we write it as minus v1, because rate of change of displacement actually is the velocity, plus because x2 is increasing with time, m2 is coming down, so x2 is increasing with time, m1 is going up, so x1 is decreasing with time. We write it as plus v2 equal to 0. From here we get v2 equals v1. Same way, if we differentiate it again, then we will say a2 equals a1. So now we have found the relationship between a2 and a1. Our equation was coming out to be m2 minus m1g equals m1 a1 plus m2 a2. But now we have a2 as a1, so this thing becomes a2 equals m2 minus m1 divided by m2 plus m1 g. This was a very simple problem, and we could have also done it by intuition, that if first mass goes up, the second mass must come down by the same amount. However, let's try another example. Now let us try this problem. We have one pulley and we have another pulley here, and this one is attached to the ground, and here we have a mass. Let's call this mass m2. Let's call this mass m1, and this is fixed here. So first of all, we identify our masses and write and draw their free body diagrams. So for mass m1, let us draw the free body diagram. It has m1g acting downwards and the tension acting upwards. Now the thing with this problem is There are two ropes.